I want to start and provide a definition of IoT. I then want to talk a little bit about the problems of IoT data. And then we'll wrap up the day by going fast forward through a number of use cases. We're not developing 50 products individually. We're developing one product and applying it to 50 different use cases. And so we're trying to figure out what is the common theme for solving IoT in general. You've heard a lot of different descriptions of IoT. There's IoE, the Internet of Everything. There's IIoT, the Industrial IoT. In Europe, they call it Industry 4.0. And there's lots of different discussions about what IoT is, but to boil it down to its essence, it's really pretty simple. It's machine data. It's data that's produced by non-computers, non-phones, and the goal here is to take that machine data and leverage it for some sort of business use. A lot of the original IoT projects that people attempt are not doing analytics, not doing machine learning. They're just starting with the basics. How do we get data, telemetry off of my devices and put it in a state where it can improve my understanding of the real world? I'll give you a start with a specific example, offshore oil well drilling. The problem with offshore drilling is that the pipe down to the ocean is very long, and the ocean water and all the chemicals in the water basically eventually leak into the pipe. So after a while, you're not just drilling oil, you're drilling oil mixed with ocean water. The roughnecks on the rig look at the fluid, it looks black. They put it in a tanker, they send it across the Pacific Ocean till it gets to the refinery. And then the chemists in the refinery said, what is this? We were going to make jet fuel today. We can't, the quality of the oil is too low. You can imagine the cost and the lost revenue if you can't convert the raw petroleum into a final product. So what we have here is a very real scenario. When we do that, they put a fiber optic network down the hole, and then they take acoustic readings at various stages along that pipe. The acoustic readings can tell you the flow of data. It can tell you, among other things, the temperature of the data, which then can indirectly tell you about saltwater leaking into the oil and other matters. It's very sophisticated, but it is analog data. So then we convert the data to digital, and the amount of formatted digital telemetry we get is about 2.5 megabits per hour. We do a little math. We start running a 7x24 operation, and then we realize that this oil field has 7,000 wells in it in one oil field, and suddenly we're into 3 terabytes of data per week. The other interesting thing about this is that if these orange dots represent oil wells, then the green dots represent aggregation points. The blue dot represents the data center. We didn't run a fiber optic under the cable because it's just a bunch of oil wells. Your connection speed is basically 3G. So we're trying to get three gigabytes of data, over a 200-300 kilobit per second network link. This is a bit of an extreme case, but everywhere we go, we find that the data is not in the right format, the data is not in the right place, and we not only have to deal with the massive volume of data, but we have to deal with the limitation of the network. In some cases, we walk into a factory and we say, if we can do what you want, but your factory network wasn't designed for this, therefore, the first $10 million you spend is going to be upgrading your network, which puts a kind of an inhibitor on moving forward with IoT projects. Therefore, what we do is we do distributed computing. We have a thing called edge node and edge processing. We have another thing called fog processing. We move a lot of the data to the data centers, and then we have the cloud. So there are 4 different places. Now this introduces a whole bunch of really interesting things to contemplate. First off, what we're doing here is nothing until we get to telemetry. So it is the data that drives all of the processing. This represents and creates a whole new model of thinking about how you structure your software. In many applications, particularly all of the transactional applications, you're modeling a business process. It's what ERP is all about, CRM is all about, SFA, et cetera. We're not modeling any processes. We're simply trying to create software that can keep up with the onset of data. So instead of process modeling computing, we're doing data-driven computing. We have real-time data coming at us from the OT world, the operational world. The IT world is not built to handle real-time data. You know, the IT world is, I'm going to process the data, put it on the disk. When somebody gets around to doing a query, a day or a week later, it'll be there. We don't have that luxury. We're pulling data usually out of Modbus protocols on oil devices at the rate of one piece of telemetry every 20 milliseconds. If we don't grab that data, it goes away. You know, somebody asked earlier, what is the issues of IoT? There are kind of two issues that I can think of immediately. First, something like Modbus doesn't send data. It posts it in a register. We have to fetch it from that register. If we don't do it fast enough, the data disappears and we miss it. Secondly, when we fetch it from the register, we have a new problem. There is an assumption that's been made since the beginning of network that we all live with that we don't even think about. And that is, if I have data and I want to put it on a network, I'm going to address it. Think of an email or think of a text message. You know, I want to send to you and you. We've fetched data, the network has fetched data from the Modbus register. The Modbus device has no idea who's interested in that data. It's not sending the data. Who's sending the data? Who's deciding where that data is going? It has to be the network. So now all we have is a new scenario where we have data-driven computing that is completely distributed, some at the edge, some in the fog, et cetera, and we have to actually build additional capabilities into the network so that we can route the data where we think it should go because the originator of the data is not smart enough to actually do that. As we do that, then what happens is we wind up intermingling computing models, data models, and networking models so that we can actually handle the distribution of things, we can tie them all together, and we can build a system. In this model here, then, that is a combination of everything, we come to yet another recognition, and that is your cornerstone, your still point, your platform is not an application, it's not a database, it's not a server. We come to the recognition that the platform is actually the network. And in the network, then, we have to take all this data from these oil wells and squeeze it through a really skinny pipe to get it into the land-based data, data center. What we do is really obvious. So we have all kinds of things. For example, we filter the data. Let's say we're doing anomaly detection. We have a threshold. We have a normal issue. If it's not, you know, too far off of what we expect, throw it away or disregard it. Secondly, we look at differences per the comment or the question earlier. You know, if you simply, if you don't send all the temperature, which is all the data, but you simply send the temperature changes, which is information derived from the data, you can reduce the amount of load on your network by about 80%. Because the temperature typically doesn't change in measurements like this very often. We can put boundary conditions on things. And so don't send me the data if it's uninteresting, send me the violations. And then when we do send the data, then we don't send individual packets because the protocol itself takes up a whole bunch of the bandwidth of the network. You've got the delimiters, you've got the destination address, you've got the checksums, you've got all this other stuff. Pack the data. It's, you know, it's the same thing as, you know, we're all going to the movie, can we take one car instead of two cars? And so we pack that data in, and then once we can pack it, then it's efficient enough so that we can actually do compression. These are the simple things that happen when we're trying to deal with large amounts of data over limited network of networks. If you actually have a data consumer which is very close to the source of the data, then you move this stuff into the edge node, you do the computation there, and then you provide it to the local guy. When we're dealing in factories and we have a $1 million CNC machine, who is the most interested consumer of that data? It's the guy running the machine. He has line of sight of the machine. You know, it's not his manager, it's not the factory manager, it's not the MES application, it's the guy running the machine. So are we going to send it to the cloud? No. We're going to send it to the data center? No. We're going to do the computation right on the edge node. So now what we have to do is not only live with the limitation of the network, but live with the limitation of the small computer, the industrialized computer that happens on the factory floor. Why do we do this? Closed loop supervisory control systems, PID controllers, that's a PID. If you're an industrial engineer, you might have heard of it. Stands for Proportional Integral Derivative Controller. It's the coolest acronym ever. But your shower control is a PID controller. You turn the knob and there's a delayed reaction. That can be really bad if you're making engine blocks because you wind up with air pockets in the engine. Or if you're doing a Bollinger Band, various other things that we need to do in order to actually handle that data. So once we do that data reduction, then we can actually do derivatives of the data. Don't send the data, send the fact that the data was out of band, and so we need to send an alarm. In many cases, we need to convert the data to HTML so that we can do visualization. In the case of others, we do correlations or other statistics, et cetera, so that we actually have higher level information that's derived from the lower level data. For example, in the offshore oil well example, the oil guys like to look at data in what they call a waterfall form. It's a line that goes down the screen as opposed to the convention for the rest of us of looking left to right. Can you do a waterfall off of offshore stuff? Yes, you can. But what you have to do is you have to do your processing as fast as the data is coming in, and then you have to have a network that can keep up with the amount of data that you want to transmit. And we figured out how to pull the data off of offshore rigs, off the coast of Thailand, put it on the desk of the petroleum engineer in Houston with less than a 2-second delay. At that point, we're doing massive amounts of computation on massive amounts of data, and the enemy is the disk. You know, the participants are the processor and the memory, and the disk is in the network. You can't put it on a disk and pull it off. And so we're actually doing large-scale data processing and doing everything we can to avoid the disk so that we can get as real-time as much as possible. So with this capability then, what we do is we start pushing algorithms down to the edge. What do you call this software? What would you call something that does one of these functions? You wouldn't call it a complete application. And so what we've done is borrow a term from computing science, microservices. Now, historically, microservices have been services in the cloud that are co-located, that have a front end on it that allow you to actually do scale out, replication, fault tolerance, et cetera. What we've done is said, everything that happens here, whether it's a previous slide or this slide, is a service. We're going to locate that where it's best appropriate for that particular piece of computation. Now we have data-driven computing on a completely distributed model, running a host of coordinated microservices with communications between them. As a result, then, what happens is we have a networking-based system as the platform upon which we can build various microservices and distribute them where we want to go. Ultimately, and inevitably, every project we do, whether it's in manufacturing, oil and gas, which are the two big early adopters of IoT, or city infrastructure, as a gentleman from Teradata talked about, leading into utility companies and other industries, we always wind up drawing the same kind of diagram. You know, the data comes to the bottom. We have multiple stops at multiple places in order to put an entire system together.
So I understand the processing you're referring to, but you seem to, from time to time, saying it's the network. But I can say it's a workstation or a server at the edge, and the distinction is kind of.
Yeah, you're right. So excuse me, I left a step out there. So you can do this processing on Windows boxes, you can do them on Linux boxes, et cetera. You can put a computer at various places, but we run into certain practicalities. So, you know, some of our customers use a term called NAFB, which stands for not another box. And so they don't like extra boxes in the factory because they introduce new points of failure. So another step that we've taken is to actually put the software into network elements, put them in the switch, put them in the routers, so that you can have less hardware.
What does it do for maintainability of this software?
It's fine, but we have to create special environments in our routers to run software. For 20 plus years, the router has been a closed box. Nobody even knew what was in it, except it was an IP router. Now we're allowing people to put user-based software in there. And so we have to partition the memory so that that can no way affect the performance of the router and some other things. But you can do that remotely. There's lots of tools in order to, Docker tools in order to download a Docker container in there with the software that you need. As we do this work then, what we find is a very distinct difference between edge and fog. Even at Cisco, 90% of the people use the word edge and fog indiscriminately until you do your first IoT implementation. At the edge, you're talking a proprietary protocol to a device, Profinet, CIP, Modbus, et cetera, or you're reading data from a sensor. That's the first time that you see the data. And you do a bunch of a special type of processing in order to capture that telemetry and make it useful. Among other things, just as all databases have a typing system, we need to have a typing system because some of these devices are really old. You can take 2.2 from this device, 2.2 from this device, and add them together and don't get 4.4 because the mantissa and exponents are not ANSI standard. And so we have to put typing system into the network in order to do that. Let's say that you're doing city infrastructure. City of Palo Alto probably has 10,000 parking spots. We're going to build an application that makes 10,000 connections to parking sensors that cost $1 each? No, of course not. We're going to grab all the parking information from one garage. We're going to host it someplace, and then we're going to have the application connect to it across the network. That's a fog node. A fog node is when you're pulling the data together. Another distinction is if you're dealing with things like city infrastructure, we're dealing with our taxpayer dollars. If you're counting parking spots, you don't really want to do a lot of computing. What's the cost of a computer that you're going to use in order to gather that data? Really, really small. If it's a retail establishment and Starbucks is trying to maintain their FDA compliance and make sure that the freezer door always gets closed, how much are they willing to spend on that? Really small. It's important to keep spoilage down and to be compliant, but at the same time, you only charge so much for a cup of coffee. And so you see lots of cases where the edge computation is like a Raspberry Pi. We have a car manufacturer who is putting hundreds of banana pies in their factory as their edge devices, and then they're using a $2,000 computer as the fog node to aggregate it all together and to normalize the data. So we see just really obvious things. But the part of this that is really not obvious is the communication across the network itself. We all know TCP/IP. We all rely on it every day. But in the networking world, we refer to TCP/IP as a best effort protocol. Yes, from one TCP endpoint to another, it will compute the checksum. If it's not right, they'll ask for a transmission. But above that, you have applications. And between the applications and the protocol, you have an operating system. There's no guarantee that applications can get the data end to end. So we have to superimpose extra protocols on top of this. And as we work with IoT, what we found is there's some very specific things that we can do which are unique to IoT. For example, displays can only handle data at 60 hertz, or even if they could handle more, it wouldn't matter because we wouldn't be able to see faster than 60 hertz. So we're gathering data off of a CNC machine at 1 millisecond intervals. We're getting 1,000 readings per second. We only need to produce 60 of those. And it'll look like a continuous stream of data to whoever's looking at it because of the limitations of the human eye. And then even more than that, as we try to match the real-time aspect of OT to the non-real-time aspect of IT, what we realize is we may be pulling data every 20 milliseconds and feeding it into the network. The application is only capable of picking it up maybe twice a second, or maybe once every 2 seconds, right? So how do we handle that? When the application asks the network for the data, don't get it first in, first out. Just give them the most recent. Give them the last in, first out, because that's actually the most accurate representation temporally to the point in time when he actually does the query. There are some cases where we're looking for anomalies, and let's say that the application's only capable of reading the data every second, but there's a spike that's happening, and the spike may be an indicator of an imminent failure, or it may be something that's materially very important to the scenario. In that case, what we have to do is take the data and store it, timestamp it, and then as the application pulls it, do a FIFO so that it can see every single piece of information. So different applications and different scenarios require different behavior from the network. The last one here is interesting. You want to make sure you get all the data, but your application may be a remote application that's connected and there's a glitch. Some of these, cellular systems are very lossy, and so we have temporary disconnections. I'm sure nobody ever experienced that. And so if the application is down for a couple of seconds, is there a way to store the data so that when they reconnect, then there's a continuation of the data stream without any loss of actual information? Yes, but this all goes beyond TCP/IP. So what we have to do in many cases is to provide a sense of transactional integrity. We call it asynchronous transactional integrity because of the differences in the speeds between a sender and a receiver, but we put the assurance in the network so that we can actually deliver everything and not lose any information. In summary then, what we do is we start with the IP network. We distribute these microservices. We designate what software we're going to put in the edge, what the fog, what is in the data center. I know everybody likes to talk about the cloud. Trust me, the guys who run factories, they're not interested in the cloud. They're interested in 7x24, 5 nines reliability. The cloud represents, two things to them. One is a thing outside their control which may cause failures, and second, a potential point of penetration for hackers to get into their factory. And so we're still seeing a lot of on-premise stuff here as we do this. Running these microservices inside the network so that we can reduce the amount of hardware, building a fabric so that everything is connected to each other using some of the protocol capabilities that I've talked about. And then you take these locations and then you start making connections. This is how you do IoT. Across factories, across oil and gas, across retail establishments, building management systems, all kinds of things. So one of the interesting things here is that as you do this work, we many times find other additional optimizations. For example, in typical publish and subscribe system like WAMP or AMQP or RabbitMQ or Kafka, you publish and subscribe to a topic. In our system, you have to be able to subscribe to a machine. I'm interested in telemetry from that device, but not that device, even if they're the same manufacturing the same type of device. And then secondly, if the device is publishing data and nobody's listening, drop it. Don't put it on the network, and therefore reserve the network for useful information. And then in other cases, you have an application that you're trying to write as a standard IT application to capture the streaming data as it's coming at you as fast as you can. You don't really have time to do a query for every 20 or 50 milliseconds. So you need the capability to do, Oracle has a thing called continuous query language. We simply adapted that to the IoT model. And so we have a dynamic query language or a DQL so we can subscribe, and then we have a handler that comes in and is able to keep up with the data as it flows in, and then allows us to actually do some things to pre-process the data before it actually gets handled to the application. All of this is really fun. And a source of great invention and a great opportunity for us to innovate. Why do we do it? We do it because of this stuff here. The biggest traffic accident in the history of the United States occurred in the state of Tennessee a few years back. The state of Tennessee has mountains, Great Smoky Mountains. There's fog all over the place. It's the most commonly visited national park in the United States. who visits it? The crazy fast drivers from New York and Boston. So they come down, drive, like nuts through the fog and crash into people from Tennessee. The governor says, I got to do something about this. And so in addition to the autonomous vehicles that you know about, there's another movement going on, much quieter, that's called roadside connectivity, where a fiber optic is run down the road, a car drives down the road, there's black ice on the bridge, the transmission detects that the wheels are spinning, transmission talks to the road and says there's ice, fiber optic cable sends everything up in both directions in the road and tells all the incoming cars slow down. The autonomous vehicles are driven by LiDAR. That's light spectrum radar. It can't see around corners. And so if there's a bridge out, if there's a pileup, if there's a traffic slowdown, these guys want to get in front of it. And so we're going to see a connected roadway movement in addition to the connected driving. Before we got involved, there was stuff like this, and the sensors were pulling every 5 minutes, sending it back to a remote data center. We put new stuff in place, obviously, hung some industrial boxes on light poles, et cetera, and improved things a lot. This is the second largest port in the world in Europe. It's huge, it's gigantic. And we learned a few things. If the water is a foot deeper, you can put more containers on the ships. The amount of revenue that generates is measured in the millions of dollars. And so you want to pack the ships with more stuff at high tide than at low tide. And so what happens then is, this is a picture of the actual port. And so what happens then is you're looking at the water level, you're looking at the salinity, you're looking at all kinds of things in order to get the maximum amount of load on your devices, and so that you can generate the most money. That's not just artificial intelligence, that's actually cognitive computing that IBM is applying on top of the stuff that I've talked about that we do. To take another example, this is a refinery in Singapore. The oil company has upstream, which is the drilling I talked about. They have the midstream, which is a refinery. If you've ever driven by the refinery in Richmond, you see pipes everywhere. That's because they do different things on different days. I've always wondered about the pipes. It's really simple. On Monday, you make jet fuel. On Tuesday, you make 3-in-1 oil. On Wednesday, you make gasoline. And so you turn the valves differently. What happens if there's a valve that's turned wrong? It is an $8 million mistake. And so because you've consumed oil or petroleum, you created a product that has no name. You got to dispose of it. It's a big mess. So what we did is put instrumentation on the refineries. We created a map. This is right off the screen. Someone says, I want to make this kind of product. We check the valves to see if they're all lined up. If they are, green light. If not, red light. Try to take the errors down to zero. Manufacturing has the sensors. They have the industrial protocols. They have the robots and the PLCs and the CNC machines. They're all over IoT. They're the biggest initial vertical. And so people are interested in operational efficiency of their devices. They're interested in the health of their machine. They're interested in preventive maintenance. Today, data is taken off of the Phonic robots across a wide variety of General Motors factories, shoved up into the Amazon cloud. The data scientists from Phonic, which is the largest robot manufacturer, has taken a look at the data, and they can actually call up General Motors and say, in your Fort Wayne plant, you have a robot number 319 that's going to fail on Thursday. It's happening today. It's very interesting. Smart cities, yes, you want to automate your lights, you want to do traffic congestion, you want to do a number of different things. But the real issue is the electric bills of these cities is ridiculous. And so why do you keep the lights on every parking lot bright all night long? If there's no movement and no cars, then turn the lights off. And so this is an actual screen of something that we're doing with some of our automated city stuff. Video. We first learned about it in terms of security. London put a camera on every street corner when the Irish were going nuts. We then got into YouTube. We now have cameras on our homes for security, $39 from Amazon, no big deal, but they're actually turning into sensors. Their cameras can look at fluid and determine the flow and the temperature of the fluid. And so the camera is now converging with IoT so we can do interesting things we couldn't do before. Last example is something called NB-IoT, narrowband IoT. As we move from 4G to 5G in the future, there will be a spectrum of the bandwidth, about 250 kilobits, which is reserved for narrowband IoT, so that just inexpensive devices with very low data rates can use that band in order to communicate. It is projected that in the next 5 years, there will be 5 billion narrowband IoT devices that use the cellular network. I went a little over, sorry, but I got excited. So,
we can take maybe 1 or 2 questions in the interest of time, and then Jim will be here so you can ask him more questions later.
So, interesting talk. A lot of stuff I didn't know. One of the points you made is the relative sparsity or the relative the constraints on bandwidth and availability at a lot of the sites that we're sort of working with. You mentioned sort of 3G stuff, and this implies the use of a bunch of encodings and compressions and aggregation methods to make sure that you can fit the information in the bandwidth. Mm-hmm. So those information reduction techniques, they work really well where sort of it's always, you know, red, 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 red. But it occurs that during any kind of I'll use the word crisis, any kind of breakage, anything going really badly wrong, it sort of follows that the information content in those streams is going to go extreme in the Shannon sense. Mm-hmm. So data reduction methods, run-length encoding, adaptive Huffman, and so forth, they're just not going to work as well. Yep. I'm wondering what's the state of thinking on provisioning these networks, reducing the data when things are normal to make it work to accommodate to bandwidth A is a fine thing, but then when things run amok and you need the extra bandwidth, right, what sort of happens?
Right, and this is very real. For example, if you look at the telephone systems, they assume that most of us are not on our phone most of the time. And then when an earthquake happens, boom, the system collapses, right? And so you take a look at the connected roadway scenario. When do we need it the most? We need it in times of natural disaster. We need it when there is a huge pileup or an earthquake or a windstorm or a tsunami of some sort. And that's exactly the time when your worst case scenario describes. And so what the guys that are put in this place are saying is, this is not going to the cloud. I've got better connectivity between the roadway and my local servers than I have between my local servers and the cloud. I don't know anything about the cloud. It's out of my control. And so there's a number of scenarios like that where people are coming to us and say, yeah, we get all of your fancy new cloud stuff, not doing it. Factories, and connected roadway and anything having to do with human safety, they're keeping it very close to the chest.
So your microservices that you talked about, do they expose, what sort of an API do they expose? Is this like a...
Yeah, the microservices API is interesting in that we open it up to a variety of languages, C++ and C and Java and JavaScript and Ruby and Dart and Python, etc. So it's not language specific. Now, if you go across languages, then you have language mapping problems. And so what we do is all microservices talk to all other microservices through the broker that's now part of the network. And that way they can be completely independent. Functionality, they can also be independent. For example, if you want to actually do time series data and grab it at a fog node, the historian database would just be a microservice that you would put in place. But the other interesting thing is we built the system so that the reverse can happen. Because imagine a factory where you've got 1,000 devices from 200 different vendors. They all have APIs that are probably designed over the last 20 years with the no standard. And how do you turn your factory on? You have to know, power on to you and on to you and activate to you and different semantics to you. And so what we did is, instead of having a different tool for every different vendor to power things on, we allow the system to go back through the microservices, and the brokers can introspect the microservices and say what actions are you capable of. And then in a fog node, we create, guess what, a canonical data model so that we can now have a simple single user interface to control all devices across the factory regardless of vendor. So there's some very specific and special things that we do with the microservices. The other thing that happens is when you build these systems and you've got all this stuff completely distributed, how do you know it's running? So you need to monitor it. In order to monitor it, then the services themselves and the interfaces have to be monitorable. And so we built that into the software development kit so that you can build your service, and as soon as you bring it up, we'll see it on the screen.
The narrowband IoT, is it for both indoor and outdoor?
Yeah, the standards body was originally focusing on indoor. Everybody's ignoring it. It's going to be everywhere, outdoor and indoor.
Expected outdoor as
Yeah, yeah.
In your quality service discussion, you went up to very short periods of lack of connectivity. It seems like there's a number of use cases beyond that,
Yeah.
with longer periods of either unplanned or expected lack of connectivity. Like those ships that you're loading, they're 60% or 70% of their time they're not connected except with a extremely tiny satellite link.
Yeah, that's right. You know, so how long can we gather data during a period of outage? Size the disk. If you want to anticipate a longer outage, you got to buy a bigger disk. Then when you actually reconnect, you have an option. Do I want the oldest data first? Or if the disk has gotten full and, you know, what do I throw away? You throw away usually the older data and you get the more recent data so that you at least know temporally what's happened most recently. There are some options there, but at some point you get overwhelmed. You can't keep everything.
Any other questions? Cool, great. Thank you. Thanks
Okay.
a lot, Jim.